This lesson will cover optimization. The learning goal is to solve problems required finding the maximum or minimum of quadratic functions and also to find the roots of quadratic functions. The success criteria is you can formulate a quadratic equation, you can choose the appropriate method for solving the problem, and you can interpret the meaning of your values to answer the original question. Now, one of the most useful things you can do with a quadratic function is to use to model a real-world problem. Many real-world situations deal with maximizing or minimizing something. This requires a vertex of any equation being maximized or minimized. To find the vertex of a quadratic equation, one option is to place the equation in vertex form. This can be done by completing a square. The other is determining the points of the roots and substituting the vertex. Now, the steps to solving optimization problems are the following. You want to set up an equation, and you do this by drawing a picture after carefully reading the problem, making sure you have all information, determine what the problem is asking you for, what's the key variables, find an equation involving a key variable, double checking that your equation makes sense with the given problem. And you want to complete the square to locate the vertex, which is the most common method, and then relate the information from the vertex back to the original problem. If the question says minimum or maximum, you are finding a vertex. Again, this is commonly done by completing the square. If the question asks to solve for a given particular value, you want to find the roots, which is done by factoring or using quadratic formula. So our first example is the owners of an equestrian center want to use 2,400 meters of fencing to build 4 new identical rectangular paddocks adjacent to each other. We want to know what the maximum area of each paddock is that can be enclosed and what dimensions will give this area. So it's maximum. We know we're doing vertex form here. And we know we have 2,400 meters of fencing, so it might be involving perimeter. We're also using area. But the main piece of information we have here is 4 rectangular paddocks that are adjacent to each other. So we have 4 rectangles adjacent to each other. So let's just draw 4 adjacent rectangles. So that gives us the 4 paddocks, the 4 adjacent rectangles. And then we can use this information to figure out what we can do with this 2,400 meters of fencing. If we're using this much fencing to build this structure, we need to look at what dimensions we have. We have 2 lengths, but we also have width. We have width on either side, but also inside, these 3 fences are equal to our width. So we actually have 5 widths that we're dealing with here. So if I were to build this structure, we would use 2 lengths plus 5 widths equal to 2,400 meters of fencing. Now, this is, it can kind of set some perimeter, but we need area. And area, length times width. I mean, this is what we want to maximize. We don't know anything about length and width, except we can find information from this formula here. As long as we're able to find one of these variables and substitute it, we can actually do something with this equation over here with the length, with the area. So that's what we'll do. We'll use this equation, this perimeter equation we've created, to solve for one of the variables. Now, it doesn't matter if you find length or width. It literally doesn't matter. You'll find the answer both ways. In this particular case, I'm going to solve for length. So we're going to subtract our 5w from both sides. 2L equal to, let's line this up better. That'll be 2L equal to 2,400 minus 5W. Then we'll divide both sides by 2. Remember, when you divide one side out, you have to divide everything on the other side by that value. So length is equal to 1,200 minus 5 over 2W. And since we now have the length, we can substitute this length into our area formula here. So it'll look something like this. It will be 1,200 minus 5 over 2W times width. And this is factored form. But we want vertex form here. We want the vertex. So that's what we're going to do. We're going to complete the square right here. First, we're going to get back to standard form. It's quite easy from questions like this. You're just going to multiply that W in. So, and I also, when I do this, I prefer having my functions in degree order. So I have 5 over 2W squared, because W times W is W squared, plus 1,200 W. Okay, we're now in standard form. We can now complete the square to find the do that. To find a vertex. So completing the square, we need the w squared to be isolated. And when we do that, we're going to factor out this negative 5 over 2 out of w squared and w. So that gives us negative 5 over 2 w squared. 1200. When you're factoring this out, remember you're pretty much dividing. You're doing 1200 divided by negative 5 over 2. That's going to give us minus 480 w. And then we would then, to continue this, we would have to, so we could do this in one line, we're going to continue on. We would take the coefficient of w off the side here, so we have negative 480. We would then divide it by 2 and square it to get our part of our square here. So negative 480 divided by 2 squared, that's going to give us 57,600, and which we add on 57,600 and subtract. Remember, we add and subtract this to balance the equation. All right, so next we need to remove the subtracted piece from this. We have to remove the negative 57,600. When you remove it from the bracket, you must multiply it by the coefficient in front, the negative 5 over 2. So that gives us negative 5 over 2 w squared minus 480 w plus 57,600. And then 9 times a negative is positive. That's going to give us 144,000. We would then factor this remaining bracket. Remember, every single time it's going to be the variable, so w minus your magic number. Remember, the magic number was, when we were completing the square, it was the coefficient of x, or w in this case, divided by 2. So that's going to be 240, or negative 240 squared, and then we have plus 144,000. So we completed the square. We now have our vertex form, which we can immediately now see that our vertex is 240, 144,000. So this value here, we have to kind of think about what this is. This 240 we know is width. So now we have width equals 240, and this width provides us a max area. It gives a maximum area of 144,000 meters squared. That's for the entire structure. So all this around, that's 144,000. The thing is we don't want that. We want the area of each paddock itself, individual. So since it's 4 of them, we would have to do 144,000 divided by 4. That's going to give us 36,000. So we now have the area of each paddock, and then we need the dimensions. So we have width, and to find our length, we would then come back here and substitute width back in. So length equals 1,200 minus 5 over 2 times 240. And that's going to give you, when you calculate that, it's going to give you 150. So length is 150. So therefore, the max area is 36,000 meters squared with a length of 150 meters and width of 240 meters. So it is a long process, but once you get to the end, it's it is a job well done. Remember, when you're doing this, you first need to create some equation to see what you're working with. In many cases, you're going to be dealing with 2 equations. You have to manipulate one to substitute into the other to then complete the square, find vertex form, and use the vertex to find the rest of the information afterwards. So there are a lot of steps. As long as you go through the proper process of creating an equation, finding a vertex and relating information back to the original problem, you'll be fine. Now, of course, not all problems will follow this method. Another type of problem we're going to encounter will look like this. So in this case, a city transit system carries an average of 9,450 people per day on its buses at a fare of $1.75 each. The city wants to maximize the transit system's revenue by increasing the fare. A survey shows that the number of riders will decrease by 210 for each 5-cent increase in the fare. What fare will result in the greatest revenue, and how many daily riders will they lose at this new fare? So we have to look at this carefully. We have two values for each variable. We have the number of people per day, and we have cost. And the number of people per day, the original amount is 9,450, and the original cost is $1.75. So we're going to use that. Our revenue is equal to the number of tickets sold times the price. And we want a new price, which is going to affect the number of tickets sold. We have a change occurring here. And this is where we're going to create an equation from. It shows that for every 5-cent increase, the number of riders will decrease. So this is a count, something you have to count here. So to work with this, we're going to let X represent the number of price changes. So this is a problem where you're given two original amounts and they change. Well, one change will affect the other by a certain amount. When you have these kinds of problems, you're always going to have X represent the number of times that change occurs. And this is going to create for us a factored form. So the original number of tickets sold is 9,450. It's going to change by 210 each time. And the original price is $1.75, and it's going to increase by 5 cents, or 0.05x each time. So this then creates for us a factored form, which we then have to expand and simplify to standard form, and then convert to vertex form to find that vertex. So you're going to do some foiling, and expand and simplify. So this is going to give you a 16,537,000.5, and then we're going to have 9,450 times 0.05x. That's going to give us 472.5x. And then continuing on with our foiling, we're going to get 367.5x from 210 minus 1.75. And then we have negative 210 minus 0.05. That's going to give us minus 10.5x squared. And then we'll simplify this. I'm going to put in decreasing degree order, so negative 10.5x squared plus 105x plus the 16,537.5. Okay, so we now have standard form, which we're now going to turn into vertex form. Again, always a lot to do here. So remember, we're going to factor out negative 10.5 from our x's. So that's going to give us negative 10.5 squared minus 10x. We would then go ahead and take our negative 10, divide by 2, square that. That's going to give us 25. So plus 25 minus 25 plus 16. Whoops. 16,537.5. We're then going to remove this negative 25, remember to multiply it by its coefficient, so that's going to give us negative 10.5. And then maybe we can skip a step here. No, actually, need that for one more step actually. X squared minus 10x plus 25. Plus 262, 25 plus the 16,000, 537.5. And then we're going to factor this bracket here. Remember, it's going to be -5. That's our imaginary number. So -10.5 x minus 5 squared. And then we're going to add these, and that gives us 16,800. All right, from our vertex of 5 and 16,800, we have a max revenue of 16,800, and we're told that the price is going to change, or number of changes is 5 times. So we need to figure out what that price is, and the number of tickets sold. So our price, our new price is going to be $1.75 plus 0.05 times 5. That's going to give us $2. And then our number of people, number of tickets, is equal to 9,450 minus 200, whoops, 210 times 5. And that's going to give us 8,400 new riders. So, therefore, the max revenue will be 16,800 with 8,400 riders. So again, problems like this, you're going to be given 2 original values, which are then going to change some number of times. You're going to use x to show that change, and that will give you a factor form. Now, not all problems you'll have to create your equations. In some, you'll just be given the equation itself, and you'll just have to analyze it. So our last example here is the path of a model rocket can be modeled using the equation h of t equals -5t squared plus 20t plus 25, where h of t is the height of the rocket above the ground in meters, and t is the time in seconds. So first, we want to know at what height was the rocket launched. So to figure that out, we just have to say t equals 0, or we just substitute t equals into our function notation here. So h of 0 equals 5 times 0 squared plus 20 times 0 plus 25. And that, this one's always very nice and easy. That's 25 meters. So rocket was launched 25 meters off the ground. At what time does the model reach its peak height? So now we need to find our vertex. We're going to have to complete the square right here. So we have h of t equals, we're just going to go ahead and factor that already. So -5t squared minus 4t plus 25. We're going to take our -4 divided by 2 and square that. We already got that ahead of time. So that's going to give us -5t squared minus 4t. -4 over 2 is -2. Squared is 4, so plus 4 minus 4 is 25. We're then going to take the -4 out and multiply by its coefficient. It's -5. So -5t squared minus 4t plus 4 plus 20 plus 25. Factor a bracket, which is the -2, the match number we found earlier. So -5t minus 2 squared plus 45. So this information right here, we got a vertex of 245. So this allows us to answer number 2 and number 3. So at what time does the model rocket reach its peak height? That is 2 seconds. That's our vertex right there. And the peak height is 45 meters. Finally, how long does it take the rocket to hit the ground? So now we have to find the roots. The roots tell us when the height equals 0, which is the ground level. So we have to factor this. So h of t equals, and we're going to factor out -5 right away. T squared. Whoops, not that's minus 4t, and then minus 5 is nice simple trinomial that gives us negative 5, t minus 5, t plus 1. So t equals 5, and t equals negative 1. Negative 1 does not work. It's back in time, so that is, it takes 5 seconds to hit the ground. So these questions are much nicer, just need some analyzation, but when you're optimizing, these are large questions, there's a lot of steps, but just follow these steps right here and you'll be fine.